One critical addressing service that is used in today's LANs is Dynamic Host Configuration Protocol, or DHCP. There can be hundreds or thousands of hosts on a network, so the manual configuration of static IP addresses is a difficult and time-consuming task. DHCP enables networkers to quickly troubleshoot and supply IP configuration information to end devices. Network devices such as switches, routers, and servers are generally assigned static IP addresses by network administrators. However, network devices such as desktops and laptops, which may number in the hundreds or thousands on the network, need to have their IP configuration information assigned more efficiently than through static assignment. DHCP is a protocol that assigns end devices IP configuration information, including IP address, subnet mask, default gateway address, and DNS server addresses. This service can be configured on standalone DHCP servers or can be enabled on DHCP-capable routers. The DHCP process, although simple in concept, consists of many different steps that must occur to ensure proper IP configuration distribution. First, a properly configured DHCP server must be available to receive and respond to client DHCP requests. Next, client machines must be configured to use DHCP. Actual DHCP operation relies upon client-server dialog of 4 messages: DHCP discover, DHCP offer, DHCP request, and DHCP acknowledgement. The first step in the DHCP process occurs when a DHCP-enabled client boots. During the boot process, the client sends a broadcast DHCP discover message. The purpose of this message is to locate a DHCP server and begin the DHCP address assignment process. After receiving the DHCP discover message from a client, the DHCP server replies to that specific client with a unicast DHCP offer message. You may be wondering how the DHCP server sends a unicast message containing IP information to a client that does not have an IP address. The answer is in Layer 2 information. When the DHCP server receives the broadcast discover message from the client, it uses the sourced MAC address of that message as the destination address in the offer message. Before sending the offer message, the server places an ARP entry into its ARP table that links the offered IP address and the MAC address of the client that sent the discover message. After the client receives the DHCP offer from the server, it must then accept the offer. This is accomplished by the client sending a DHCP request message to the server. This message is a broadcast and can serve 2 purposes. First, it enables the client to get verification from the server that indeed it was a specific IP address that was assigned. Second, the message is a broadcast, so it notifies other potential DHCP servers that the client has accepted a DHCP address from a specific server and in effect declines offers from other servers. The final message that is sent in the DHCP process is the unicast DHCP acknowledge message sent by the DHCP server. The DHCP acknowledge message serves as the final confirmation that IP configuration has been bound to a DHCP client. After the acknowledgement is received by the client, it begins using the IP configuration information to function in the network. The amount of time that a client uses the IP information depends upon the lease time, which is configured on the server by a network administrator and supplied to the client at the time of the address binding. Cisco routers running specific iOS versions support DHCP services. When configuring DHCP services on Cisco routers, you begin by excluding IP addresses that will be statically assigned to routers, switches, and other servers. This can be done by specifying a range of addresses or a single address with the IP DHCP exclude address command. The next step in configuration is the creation of address pools from which IP addresses will be distributed to clients. When the IP DHCP pool command followed by a pool name is entered, the CLI enters DHCP configuration mode. Note that multiple pools can be configured to supply address information to multiple subnets. When in DHCP configuration mode, you can specify the address range that makes up the pool. Notice that the address range of the pool includes addresses that are excluded. However, because those addresses have been excluded, they will not be distributed to end devices. Other tasks that can be completed in DHCP configuration mode are the specification of the default gateway address of the pool and the domain name. Other, more advanced configurations not shown here include specification of address lease time, DNS server address, and NetBIOS WINS server address. Earlier, we stated that multiple pools can be configured to distribute addresses to multiple subnets. However, this scenario does require additional configuration. Recall that the initial DHCP discover message sent by a client is a broadcast message. Also recall that routers by default do not forward broadcasts. This presents a problem because standalone DHCP servers, as seen in this graphic, will not receive DHCP discover messages that originate from a subnet different than their own. In order for the server to receive these messages, the router that is blocking the broadcast must be configured as a DHCP relay. This is done by using the IP helper address command. The IP helper address command is configured on the router interface that receives the broadcast from DHCP clients and is followed by the IP address of the DHCP server. This concludes our presentation of the DHCP process. A thorough understanding of this process is critical for all networkers. Knowing the specific messages, what information they carry, as well as concepts such as DHCP pools, relays, leases, and excluded addresses, will enable you to effectively implement and troubleshoot this deceptively simple protocol.